So my talk is on the green approach towards a transparent and conducting film for optoelectronic devices. But my talk will also move into other ways in which we have used nanotechnology in the various applications. So I'll talk about how I've used nanotechnology in electrochemistry and also in water remediation. So if you live in South Africa, you will know that we have a problem with our energy system, and more people are relying on solar panels. And so most people can't afford solar energy or solar panels, so that excludes a lot of people. But solar panels don't come or they come with challenges. And one of the challenges, besides being expensive, is that they break. And we know that we've got hailstorms, and they also are prone to have water damage, and they can also be damaged by dirt. So nanotechnology can have solutions to those problems. And we find that nanotechnology solar panels can actually have reduced manufacturing costs, and also they are robust because nanotechnology solar panels can offer quite flexible solar panels. And that is our aim in this project. Our aim is to fabricate solar panels that are flexible, that are transparent, and that are conductive. And in my projects with my students, our intention is to replace the ITOs and the FTOs that are extremely expensive. And the intention there is to use cellulose as a flexible alternative to these common metal oxide transparent conductors. And it is because we know that cellulose can actually be fabricated into transparent and flexible films. But now the drawback to cellulose is that it is not conductive. And that is where the magic of nanotechnology comes in. Now, cellulose can actually be formed from trees or from algae or from bacteria. So what we do is that we actually just brew tea. The normal kombucha tea that you get from the coffee shop, what we do is we supplement it and we grow SCOBY, the SCOBY that you would also grow or brew when you make the kombucha tea. And that is the insert that you see there. And SCOBY is actually a cellulose mat, and it is filled with bacteria and fungi that you eat, and we grow it, and it's bacterial cellulose. So what we do is after we've grown it, we take it and we biosynthesize it using an HS medium. And this HS medium is basically what? Algae, not algae, it's phosphates, sulfates, that is used to biosynthesize further the bacterial cellulose. And after we have biosynthesized our bacterial cellulose, we then clean it, we hydrolyze it, and we then process it further. And that is how it looks like under a SEM microscope. And we had hoped that after that, we would then grow our we would have grown our film from our bacterial cellulose. And this is how it looked like after we had processed our film. So what we discovered is that our fiber or our polymer was not that impressive, in that it was quite brittle and it did not form the film that we wanted it to form. So since our polymer was not behaving, we then had to come up with ways in which we can make it behave. And the only way is that we had to reinforce it with another polymer. And that polymer was, or those polymers that we decided to choose was PVA and PEO. So we reinforced it, but we made sure that we had more of our BMF than our PVA and our PEO. So this then depicts, this image just depicts how visually transparent our films were after we had reinforced it. So we were quite happy with our product, and the image or the spectra here shows how transparent our images were after we ran the transmission spectra. So here we show, this is the BMF. So this is just our film, our bacterial film alone. So it gave us a 90% transmission, but obviously we know that it was quite brittle, so we could not use it. So after we've reinforced it, so this was reinforced with PVA, we did get a decrease in the transmission, but it was a slight decrease with PVA. But we saw that when we reinforced it with PEO, we got a quite significant decrease in the transmission. So we got what, 70% from 90% decrease when we reinforced it with PEO. It's not that bad, but we did get nicely formed films. Because our films were not conductive, because the plan is to make conductive, transparent, and flexible films, because the plan is to replace the dreadfully expensive ITO and FTO conductors. So then we had to make our nanoparticles, and we chose to make silver nanowires because we found that they work quite well in making our films conductive. So these are the nanowires that we used, and this is the transfer method that we used to coat our films, and we used different amounts to coat our films, and that is the transfer method that we used. And this is how the optical transmission changed upon coating of our films with our different loadings of the nanowires. So it wasn't that bad. Then we compared the ITOs and the FTO. So we can see that we get quite good comparison if we compare the ITOs and the FTO. So we can see that if we add, say, for example, a higher loading of 0.50 milligrams of the silver nanowires, we get close to 60% transmission. But if we load about 0.15 milligrams of the silver nanowires, we get about, let's say, around 75% transmission. So we had to play around the different loadings of the nanoparticles on the films to get a good transmission of our films. We also then needed to test the mechanical strength of the films, because we also want our films to be flexible, because we don't want the films to break just like the FTOs and the ITOs, because when the hailstorms hits, we don't want to have breakages. So we did the stress strain tests. We actually used the equipment from the food scientists, so it's food science department. So it's very important to know what the other departments have in terms of the equipment, because you never know what they have that could help you. So when we looked at the bacterial cellulose alone, this is what made us see that they're actually quite ductile and they're not good on their own, because as we loaded stress on them, we saw that when you stress them, they easily break, as we can see from the curves as you apply stress on the films. But however, when we added the PVA and the PEO, we could see that we do not get the same curve. So they acted like they are a plastic, which is exactly what we wanted. And we could also, by just bending them, we could bend them, we could, drop them on the floor and they wouldn't break. So they were acting like a plastic, as the stress strain curves could tell us. So that means that mechanically our films, upon reinforcement with the PVA or the PEO, they were quite good. And we also looked at the resistivity, because obviously if your resistivity is high, that means you have a poor conductor. And we looked at if we increase the loading of our nanoparticles, we saw that if we have a loading of, let's say, 0.2 all the way down to 0.5. Obviously, we don't want to have a loading of 0.5 because that then compromises our optical transmittance. But if we look at a loading of 0.2, our average resistivity is quite low, which is good. And well, if we look at our optical transmittance, it's still okay if we look at where our ITO and FTO is. So, I mean, that's a good compromise. And I mean, it fares well if you compare it with the ITO and FTO. And this is for, I think it's for the PVA film. And if we look at the PEO film, again, the 0.2 loading fares well if you compare it with the ITO and FTO twins. So resistivity there is around 10. And then if we look at, that's the 0.2 loading of the nano wires. So, I mean, overall, we've got a good system here. I mean, we can stop buying these expensive twins. So we were able to produce flexible, conductive, and transparent films. So now we're looking at trying to scale up and start using them in other applications, such as the photo electrochemical splitting of water, because there we also use these horrible twins over here. Now, if I can just change gears a little bit, if you were watching the news last week, the Department of Water and Sanitation is suing itself for providing residents with dirty water. I mean, this picture was taken at a municipality in Kukune in Limpopo. The lady here has water that she's taken from this river where they share this water with animals. So I think as nanotechnologists, there's something that we can do here. I mean, when she goes home, there has to be a tool that we come up with to say, okay, there's the water, I mean, there's nothing we can do while ANC is busy, taking themselves to court. There's something that we can do there to say, okay, there's this water that you have. What tool can we give this lady to say, take this thing and purify this water with this tool that we have developed as nanotechnologists? So in that sense, some of the research that my students and I have been doing is in water remediation. And I'm just going to tell you briefly about just a few projects that we've been doing. So Prisan, what she did was she took iron oxide and coated it with chitosan and graphene. And she made this composite where she wanted to remove chromium from water and use a magnet after she has removed the chromium to remove all that gunk out of it. And she made her composite in two forms. The first, it was in the form of beads. Not such a nice picture, but that was in the form of beads. And the second was in the form of flakes. So that's how her beads looks like under the microscope. And that's how her flakes look like under the microscope. And then Ronald's from Zambia. So when he came to me, he says where he lives, it's Cab, where it was, I don't know what year it was, but it was the most polluted in terms of lead polluted city in the world. So he said he wanted to come up with a way in which he can try and remove some of the lead in the water. So he came up with this project. He says there's a lot of moringa in his town. So I said, then use that moringa in a way in which you can come up with a way to use it to remove this lead. So we use that biomass incorporated with the polymer and iron oxide, and electrospun that, came up with his nanofiber mats, and he used that as a lead, or to remove lead in water. So he's currently sampling water for lead removal. He's in Zambia now. So that's what he's doing. And then Lebo, this is part of his project. He's using MOFs, and my nanocellulose is using, I love cellulose, so he's using crystalline nanocellulose to incorporate it in his MOFs, and he supported that with cellulose acetate to form his film. And this is the cross section of his film, because his film has to be porous, because he wants to make his film and he wants to use his film to remove dyes in water. Because when there was the COP27, was it, I can't remember, it was in Egypt, he found out that the textile industry is actually a culprit, and they are polluting with their dyes, they're polluting water. So he says he wants to remove dyes from water, and I'll show you some of his results in the next slide. So these are some of the water remediation projects that we have undertaken in my group. So this is part of Chrisanne's work. So these are how the beads looks like under the microscope. So this is how she mapped the beads. So the chromium is what you would see in blue. So this is after she has done the adsorption. So you'll see the blue dots there represents the chromium. And after adsorption, you will see there are hardly any blue. So you can see that there is no blue that has been picked up. So that is after adsorption. And then there's Lebo with his film that he has made that you saw in the previous slide. And then he used it to pick up chromium, I'm saying chromium now, to pick up methylene blue in water. And then you can see how it has completely, well, not completely because UV still picked it up, almost completely picked up methylene blue in water. And there it is. We just can't remove it after that. So, but it's fine. It's a cheap process. We are using crystalline nanocellulose, and we are using cellulose acetate. It's a cheap process, MOF5. It's easy to make. But we are trying to find solutions for that lady who is using water that is also used by animals. And then if you allow me to shift the gears again, just for the last time, if you are a lover of fast foods, you are having a problem again, researchers have found, well, we are researchers too, but there are phthalates in fast foods. So if you like McDonald's, Burger King, and Pizza Hut, there's a bit of a problem there, because 30% of the foods have found to contain phthalates. And these phthalates have been linked to reproductive health problems. So we know that phthalates form part of the pesticides, or what are the containers that are used to house your foods, your fast foods. They have now seeped into the foods that you eat. And we know that phthalates are part of the endocrine disruptive chemicals. So they disrupt all the hormones that are used to develop your body. So if you feed your children McDonald's and all of those things, you are messing them up somehow. So part of the the research that I do is I do electrocatalysis or electrodetection using nanoparticles, and these are some of the nanoparticles that I use. I use very cheap materials because I don't believe in expensive research. So it's mainly metal oxides, nanoparticles. I use composites of metal oxide nanoparticles. I use phthalocyanins. I use phthalocyanin composites, as well as POPs. So we synthesize POPs, I make them. I like polymers. I discovered I incorporate or I enrich them with metal oxides, and they look absolutely stunning. So especially when I've enriched them with a number of other nanoparticles, I find that I get very, very good detection, very, very good results. So we detect endocrine disruptive chemicals such as phenols. These are MSCs, PhDs that do this work. We also make our own electrodes, but I think that with colleagues from Mintech who have screen printed electrodes, we shouldn't have electrodes that look so rough. They must come on the table and help us make screen printed electrodes so that we don't have to have bad looking electrodes. We still do get good results from such systems. We've proven that we can make them, so they can assist us with making good electrodes that we can, use. We also, with using our nanoparticles, are able to do simultaneous detection of metals. Now imagine if we have electrodes from screen printed electrodes, not these rough looking electrodes, but the magic of nanotechnology that can be unleashed from that. So without taking much of your time, nanotechnology, can be used in catalysis, in water remediation, and in energy applications. So with that, I'd like to say thank you, speaker, and thank you, colleagues.